Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencaster.com/pricing and use my code Breaking Math, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your. People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencaster.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story.
Today's episode was recorded with masks on. Please excuse the quality as we continue to battle COVID. There are a lot of things in the universe, but no matter how you break them down, you will still have far fewer particles than even some of the smaller of what we're calling the very large numbers. Many people have a fascination with these numbers, and perhaps it is because their sheer scale can boggle the mind. So what numbers can be called large? When are they useful? And what is the Ackermann function? All of this and more on this episode of Breaking Math. I'm Sophia, and you're listening to Breaking Math. With us, we have on Diane Baca, my mom.
Hi, everybody.
And she's been on a couple other episodes, the Game Theory one, the Great Stratagem Heist. But before we go into the topic of today's episode, which is large numbers, I'm going to do a few plugs. The holidays are coming up, and it might arrive a little bit late if you are hearing this podcast, but our Facebook poster store is back online, and the poster is $15.15 plus shipping and handling, which is $19.65 within the United States. If you want to donate to our podcast regularly, we have a Patreon at patreon.com/breakingmath. That actually helps us quite a bit. The littlest amount, $1, $5 you could do. If you donate $22.46, you can get a poster with that. But if you're a patron, you can have outlines from the show, and we have the episodes there without ads. If you want to find out about the show, just go to our Facebook page and find out updates about the show, or on Twitter at Breaking Math Pod. Our website is at breakingmathpodcast.app, and we have a sister podcast, Turning Rabbit Holes, that you can go listen to. But yeah, so large numbers. What do you know about large numbers?
Me, I know that they are the really large numbers we assign names to. We do large, I guess, very small numbers, which could be considered very large small numbers. We do say Avogadro's numbers, so I know that those exist.
And that is 6.02 times 10 to the 23rd, right?
Yes. So I know that we do name numbers, and we figure out a way to talk about them, I guess is what I'm thinking.
Yeah, and that number is, it's pretty big, obviously, but we're going to be dealing with some insanely big numbers today. But as a quick outline of the show, we're going to go through some early examples of large numbers. We're going to talk about Google, Knuth's up arrow notation for denoting large numbers, Graham's number, and the Ackermann function. All right, so in early Greece, they had the concept of a myriad, which meant both 10,000 or basically indefinitely large. And we still use that same use today.
It's funny, we use it just to describe a bunch or a big selection of things. Oh, they had a myriad of that. Yeah.
Yeah, and they did use this usefully, but obviously it'd probably be for tributes and stuff like that. But it was an M with a bar over it or other numerals over it. So if you had M with the Greek numerals for 234 over it, it would mean 2,340,000.
So they actually had a concept of 2 million back then?
Oh, yeah, they did.
They didn't have a need for it. Well, I shouldn't say they don't have a need for it. I'm just wondering what their need was.
In trade, they probably needed to use it.
2 million?
Because I know that they were probably dealing with large quantities of, at least shells and stuff like that.
2 million's a lot, though. You think about it. It's kind of interesting that they had that concept.
Oh, yeah, but if you think about it over the course of a year, it's it's like 3,000 things a day is a million a year.
Okay, never mind. That is pretty much, that makes sense then, yeah.
But yeah, the Mayans also had a concept of very large numbers. The long count calendar, for example, has 1.678 times 10 to the 31st days in it.
What is that? Long count calendar?
It's it's cycles within cycles. Like the date of creation is supposed to be about halfway through, which is 13.13.13.13.13, and then there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 20 13s in a row.
So I don't understand. Why are there 13.13.13? I've never seen a number written like that.
Oh, it's in base 20.
Oh, so you're saying...
And it's a calendar. And it's actually base 20, except for the second digit from the right, which is base 18.
Well, why wouldn't it just be counting to... If it's base 20, why wouldn't it be going up to 9? Wait, why is it going
That's just the date of creation. So it could be 19... another valid date of creation would be 19.18.2.3.
That is so weird to me. I can't even get a concept of that. Even the 10 to the 31 is impossible for me to imagine.
Yeah, that's huge. Far longer than the universe has ever existed. It's longer by basically if every day would have to be about as long as the universe, and then even then you wouldn't be adding up to all of this.
That particular number? Wow, that's huge. Days. I was going to ask you how many years that was, but
yeah, because 10 to the let me see how many years. I'm going to calculate it as slightly wrong. It is 1.51 times 10 to the 31st days, but still. That is 4.137 times 10 to the 28th days. Years.
Oh, heck.
Which is...
That's into the illions that we don't even talk about.
Yeah, which is... that would be a billion, 10,000 million years.
That's hard to understand. This is why I guess we need really large numbers.
Yeah, and that's the thing about them too, is that they really are kind of impossible to understand. It's just that we just kind of know that they get bigger and bigger. And we run into them in usually in situations where, counting things, I've noticed. One number that we're going to be talking about later, Graham's number, is found in Ramsey theory, which is counting the number of possible solutions to. So it's like saying how many different combinations would I need to come up with this outcome, basically.
Right. So they're counting combinations, or in the case of Avogadro's, you're counting tiny things, like atoms. Or I guess they probably use these things in universe counting, or in stars or whatever?
Well, even stars, there's only the number of particles in the universe that we'll be talking about in a second, but even that is not as high as you might think.
So I guess I wonder why we need to create these numbers when they really don't exist in the world, or
Well,
maybe they do.
it's for measuring mathematical concepts.
Oh, okay. Never mind.
But the ancient Indians had maybe the biggest concepts of large numbers amongst ancient people. For example, they had the bodhisattva, which is 10 to the 1 dodecillion about.
Dodecillion?
Yeah, 1 dodecillion, 37 undecillion, 218 decillion, 383 nillion, 881 octillion, 977 septillion, 644 quintillion, 441 quadrillion, 306 trillion, 597 billion, 687,000 million, 849,648, and then I missed one somewhere because there's 128 after that.
That's crazy.
But yeah, it's these are used for religious purposes.
In what way?
Counting numbers of days. I mean, the Lalita Vista Rautra is 10 to the 200 infinities, which is Google squared.
So the idea is that it's infinity.
Yeah, I think it's just meant to boggle the mind and meditate on.
Okay, that would make sense because it does mine.
And then Paro is 10 to the 400 quadrillion infinities. And 10 to the 400 quadrillion means 1 with 400 quadrillion zeros after it, which would take basically thousands and thousands of hard drives just to hold the zeros.
I was going to say, like, that's not even something you could write. It's purely a concept.
Google is 10 to the 100th power, which is just 1 with 100 zeros after it, and is actually the first large number that I was aware of. And Google, it's spelled Googol, and the company is only named after it. But just to talk about how big of a number just this is, there'd be less than a Google of atoms of hydrogen if all of the dark matter and the matter in the universe were converted to hydrogen. You would have to basically take, for every hydrogen atom that was made out of the mass of the entire observable universe, you'd have to replace it with as many fish tanks as it would take, 10-gallon fish tanks that it would take to fill the ocean.
Wait, whoa.
And that's a Google.
So you're saying basically if we broke everything down in this universe and we split it back into
hydrogen.
Molecules of hydrogen, which is just one atom or one.
Yeah, and we're talking about matter and dark matter, and remember that matter is only a small percentage of dark matter.
Actually, yeah,
matter.
That's a whole nother thing for me. I'm not aware of. I don't really know a whole lot about dark matter, so
Nobody
I'll just accept it. Okay.
That's basically what the physics community did. It's like, oh man, dark matter exists, so I guess we have to accept it.
Okay, I'll take that. Oh my gosh, so that's really crazy. Basically, you're saying that. Oh, I didn't get the fish tank thing. So you're saying what?
So let's say now we have all these hydrogen atoms made out of the old universe.
Okay.
Now we take each one of those hydrogen atoms and we replace it with as many hydrogen atoms as it would take 10-gallon fish tanks to fill the ocean.
Oh, that's a weird concept. Okay.
I couldn't find it's hard to talk about these numbers.
Well, especially 10-gallon, to imagine how many 10-gallon fish tanks in the ocean, that's not even conceivable either, because that's crazy, right?
Yeah, because it's about 10 to the 20th, and it's really hard to talk about that number.
I know, it's crazy. These numbers are really big.
And that's also the thing. It's like astronomers have this problem where they're talking about these large objects and they can't really wrap their heads around how big they are. I mean, even the Earth is too big for humans to really comprehend.
Yeah, yeah. And maybe that makes sense. The reason why you said, that they sometimes incorporate it into religion. It makes sense to me now, the undefinable, the unachievable or not understandable.
The far away.
Yes.
And then we got to talk about Googleplex, which is 10 to the 100th.
Why did we need that?
Because it's one with a Google zeros after it. We didn't need Google.
I guess we just have to do stuff like this, huh? Okay.
Yeah, and if we all just stopped using Google, maybe Google wouldn't have as much control over everything. Get the number.
Little editorial there.
No, it's not an editorial. I'm just talking math.
Oh, okay.
Yeah, I'm just talking about, if everybody stops searching for reasons to use Google everywhere. So now we're going to talk about much bigger numbers than that.
Because they need to exist as well. Okay.
So we're going to talk about Knuth's up arrow notation. And from what I could tell, it was just invented for fun.
For me, Google was just created for fun, and a Googleplex was created for fun. I mean, if it doesn't really apply in the world that we live, do we really need it? Or is it just for fun?
Oh yeah, most math starts out just for fun. I think that's what Newt's up arrow notation is because, this reminds me of like when I was a kid because, he said, okay, addition repeated is multiplication, repeated multiplication is exponentiation. Well, what's repeated exponentiation? And it turns out that is two up arrows in Newt's notation. So for example,
Oh, okay, I got you.
yeah, so like two up arrow three would be 2 to the 2 to the 2, which is 16.
Wait, but two to the third is 8. And then you're saying 2 to the third to the third?
No, two up arrows because that's a new notation. That's not like two exponentiation marks. It's two up arrows.
So, and that means, how does that equal 16? What are you exactly doing there?
Because
2 to the 2 is 4.
and then 2 to the fourth is 16.
Oh, okay. Oh, okay. That's a new notation. I've never seen this before.
And then two up arrow 4 would be 2 to the 2 to the 2 to the 2, which would be 2 to the 2 to the fourth, which would be 2 to the 16th, which is 65,536.
Oh my God, that's so weird. It's kind of hard for me to get it. Like, so you did 2 to the up 3 is 2 to the 2, which is 4.
Oh, remember exponentiation reduces from the right.
Oh, so it's 2 to the fourth, and that's why it's the 16th. If I know that it goes to the right, that makes more sense.
Yeah.
So 2 up fourth. So what is that actually saying? 2 to the fourth to the fourth to the fourth?
No, it would be 2 to the 2 to the 2 to the 2.
Oh, and that's 2 to the fourth to the eighth. 2 to the eighth?
No, wait, no, because 2 to the 2 to the 2 to the 2, right?
Yes, and so you go from the right side in.
Yeah, so 2 to the 2 on the right side is 4, right?
Oh, and 2 to the fourth is 16.
And 2
I got
to the
you.
16th is...
I got you.
Yeah.
Okay, so you go from the right, 2 to the 2 is fourth, 2 to the fourth is 16, and then 2 to the 16th. I get it. Yes, okay.
Yeah, it's 65,536.
So yes, if you write this out, 2 to the 2 to the 2 to the 2, and then start from the right-hand side, it's so much more comprehensible.
Yeah, and then, but then, if you have, and then you run into really big numbers really quickly. For example, 2 with 4 up arrows and then the number 4 is 2 to the 2 to the 2 to the 2. And
This is the story of the one. As a maintenance engineer, he hears things differently. To the untrained ear, everything on his shop floor might sound fine, but he can hear gears grinding or a belt slipping. So he steps in to fix the problem at hand before it gets out of hand. And he knows Granger's got the right product he needs to get the job done, which is music to his ears. Call, click Granger.com, or just stop by. Granger, for the ones who get it done.
then there's 65,536 twos.
Oh, wow.
And that's way bigger than a ghoul.
And basically, this is just his up arrow notation. It was a his. Knuth is a his.
Yeah.
Okay. It was
Donald Knuth.
Who? Dobble?
Donald.
Oh, Donald. Sorry.
Donald as in duck.
As in duck. Yes. Donald Knuth. Oh, okay. That's crazy. That's kind of fun though. I can see how it could be fun.
And then you might wonder, what is 0 with n up arrows to the b?
1.
Well, it turns out that it's either 0 or 1. If it is 0 when n is 0, it's 1 when n is 1 and b is 0. It's 0 when n is 1 and b is greater than 0. So like 0, up arrow 3 would be 0.
Wait, just real quick. I forgot this. What is 0 to the 1 power? To the power of 1?
0.
How can it be 1 then? How can it ever be 1? Is it 0 to the 0 power is 1?
Yep, 0 to the 0 is 1.
Okay, I knew there was some kind of weird definition that I forgot. Yeah, okay.
And it actually turns out that it depends if b is even or odd. So if like n is greater than 1, then it's 1 when b is even, and it's 0 when b is odd.
Wow, this is so much easier to understand if you could see it. Wow.
Yeah.
So you're exponentiating. I get it. You're exponentiating the n and the b.
Yeah, and then you're using n up arrows. So if we have like 0.
Oh, I got you.
Yeah, so like 0, up arrow 4 would be 1 because 4 is even.
I got you. Okay, that is crazy. And that's just for fun.
Oh yeah, that's just for fun. That's just what the math shakes out to be.
It's like a mind game.
So now we're going to talk about the horror that is Graham's number.
Confession, I've never heard of Graham's number.
Most people haven't.
Oh, really? I hadn't heard of Knuth's up arrow, but...
Yeah, Graham's number. So the problem is this. You have a hypercube, right?
Okay.
So hypercube is basically you could imagine it as you you have a square, right?
Okay.
If you connect two squares by their respective vertices, then you get a cube, right?
Well, two squares if you connect them? Yeah.
And then think about if you connect the corners too. So there's a bunch of X's everywhere.
Okay.
Now, if you make two of those and you connect the respective vertices together and across the X's just like you did before, then you'll have a four-dimensional hypercube, even though it's like in 3 dimensions made of string. And you can keep doing that. It'll be this big tangle of wire, right?
I'm going to say yes.
I mean, not wire, of like string.
Whatever, yeah.
So imagine the string are either red or blue.
Okay.
So the problem is this: what dimension does this hypercube have to be so that no matter how we color the strings, we choose whatever red or blue we want, there will be at least one square with an X in it that is all the same color.
I'm going to accept that. What is the point of that?
Well, that's the problem.
Oh.
See, the problem is what is n? Like, what is
that number that'll give you that square with the...
Yeah, so like how many dimensions would there have to be? And it turns out that the lower bound, as of 2008, is 13. So it takes at least 13 dimensions, but it might be a lot higher than that, quite a bit higher than that. And an early solution to an upper bound was Graham's number. And to define Graham's number, we have to define Graham's numbers. So G1 is 3, 4 up arrows, 3.
Oh, hey. Okay, so this did turn out to be useful in some ways. You're using that other...
Yeah, Newth's
You're
arrow notation.
using Newth's arrows in order to describe Graham's number.
Yeah, and as you can see, as you can imagine, that would already be an immense number, right? 3,
Sure,
4 up arrows, 3.
absolutely, yes.
Now, G2 is a 3, right?
Wait, what is G1, G2? Sorry.
G2 is defined in terms of G1. G3 is defined in terms of G2, and so on until we get to G64.
What is G1, though?
G1 is just 3 with 4 up arrows and then 3.
But I mean, what does the G stand for? Like, what does that mean?
Oh, it means like Graham's number.
Oh, it's his first. Oh, okay. I'm sorry. Okay, got you. So Graham's number 1 is 3, 4 up arrows to the third.
Yeah. And now G2 is 3 with G1 up arrows.
Got it.
To the 3.
Oh, wow.
So there's literally this almost infinite number of up arrows.
Insane. Okay.
G3 is 3 with G2 up arrows and then 3.
Okay, we are so big right now. That's no way.
And then you keep going and going and going until you get to G64, which is 3 with G63 up arrows and then 3.
And what does that prove, that G64? Like, what is that?
Well, G64 is, it was an early solution to an upper bound for Graham's number. So it takes at most that many dimensions and no more.
Okay, I'm just curious. As of right now, Graham's number was talked about in 1971.
Yeah, and that was the number of dimensions that the maximum was.
And somebody figured out in 2008 that the lower bound is 13?
No, the lower bound is still 13, but the upper bound at the time was known to be about 6.
Okay.
But it was between 6 and G64.
Oh, I see. Okay.
So it's either one dun 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 or some number that is like massive and Cthulhu-ish.
Cthulhu-ish.
But now the upper bound is much, much smaller, but is still mind-bogglingly huge, which is the number of dimensions that this hypercube must be is 2 to the up arrow 5,138 times 2 to the up arrow 5,1040. Take that and up arrow it twice to the 2 times 2 to the double up arrow 5,137.
Do you think anybody really ever has a concept of this? Because
no, it's all a game. It's a math game.
Okay, because I was like, that's way bigger than a Google or Googleplex or whatever.
Oh yeah, it's insanely big.
Okay.
Yeah, but it just happens to be way, way smaller than Graham's number, which is just ghastly. It's horrifying. Because remember, Graham's number is describing a number of dimensions. And in an n-dimensional hypercube, there's 2 to the n vertices. So there'd be 2 to the G64.
Whoa. Okay. Yeah, that's massive. That's so huge.
Yeah, and that's kind of how I kept like thinking this whole episode. It's like, oh, wow, this number, it's so big. It's just a big number. That number. And then I got kind of like, after a while, I was like, oh, this number, yep, it's a big number. Like, I don't understand these numbers. Nobody does. I mean, even a Google is bigger than anyone can comprehend.
But it's a method of I guess, playing with the mind.
Oh, yeah, it's playing with the mind and playing with the nature of math.
Yeah. Okay. That makes sense to me. That makes sense. Yeah. I do remember when you learned to Google, by the way.
Oh yeah, and I kept
do.
writing it everywhere.
Oh my God, you kept talking to me about it and writing it everywhere on paper and everything, and it was very exciting to you. I do remember that. I remember thinking, I didn't know what a Google was.
All right, so Ackermann's function generates extremely large numbers, and that's its whole deal. And it doesn't really have uses other than to show some stuff about tail recursivity. It's more of a tool. But tail recursivity and simple recursivity, I can't remember the exact definition. We might have a episode soon on recursiveness and also sets. But basically, the Ackermann function is defined in terms of itself, right?
I don't know.
Okay, so the Ackermann function is at A0n. So A0n, it's a two-dimensional function. It takes in two variables. So A of 0 and n is just n plus 1. That's the definition 1, right?
I guess that is.
It's piecewise.
I can see it. I can see it written down.
Yeah.
So it's basically a function called A, which is Ackermann. I'm assuming that 0 is defined, n is not. So it looks like it's taking in just one number. But
yeah. So now now the first argument is greater than 0, so it's m plus 1.
Okay.
And the second argument is 0, then it's the Ackermann function of m and 1. And so far, it doesn't seem to be that horrifying.
To me, it just seems like letters and numbers right now. A bunch of letters. And the point is to generate large numbers?
Yeah. Well, I mean, it's also just kind of a fun one because it just explodes so quickly. Sometimes mathematicians have competitions of this sort. Like, hey, I'm gonna make a function that explodes quicker than your function, and it's gonna be completely novel in its construction.
Oh, okay. Okay, that makes sense to me. I was going to ask you who uses this. I mean, is it applicable in any kind of...
I've never seen any application for this.
Okay, so this is simply math. It really is math defined within the math community or mathematicians or whatever you want to say.
Yeah, but also, I mean, as we talked about on the show, the things that didn't have a use for a very long time sometimes end up having uses hundreds of years later.
I mean, that's true. Okay.
But but the Ackermann function of m plus 1 and n plus 1 is a to the m and a to the m plus 1 and n.
So do you put this visual stuff up on the website so people can actually see what you're talking about?
Not always, but I might do it for this episode. And that outline will be available on facebook.com/breakingmathpodcast. Okay, so the Ackermann function of 0 and 0 just happens to be 1.
Okay.
The Ackermann function of 1 and 1 is 3.
Okay.
The Ackermann function of 2 and 2 is 7. And the Ackermann function of 3 and 3 is 61. So it doesn't seem to be growing that fast.
No, not really.
But the Ackermann function of 4 and 4 is 2 to the 2 to the 2 to the 65,536, all minus 3.
Oh, you have to throw in that minus 3 there. Okay. But that doesn't tell you what the function is.
It's kind of hard to work. That's actually one of the things that when I learned the function bothered me about it was I was trying to think well, what does it mean? And it just turns out that it just can be described with up arrows, but it doesn't really mean anything. It just grows extremely quickly.
But I mean, how does it grow? In other words, there's no function that you're plugging it into, or is it a visual function? Like you're just creating a pattern of some sort?
Well, basically it's not like a function you could really plot. It's like a function defined in terms of itself. So you can think of it as an operation almost. So multiplication is a function that takes in two arguments.
That's true. Okay, I get that.
So it's just a very abstract operation. Like, for example, the Ackermann function of 2 and 3 is a number with 18,728 decimal digits.
So how'd you find these numbers? Are they defined somewhere? Like, how did you figure out Ackermann function of 2?
I just found it on Wikipedia. But these values, the way that these are done is by analysis. It just very careful, chipping away at stuff. So everything has slightly different values.
Yeah, because 2 is 7, and then 2 3 is this massive number.
I mean, let me show you the table of Ackermann values on Wikipedia, and then you can see what I mean.
Okay. Okay, so looking at this function. Oh, wow. Okay, so it has to do a lot with the up arrows again.
Yeah, the up arrows feature prominently.
Okay. They like the Newth arrows and the Grams numbers. That's funny. So it's as if they just thought, we're hey, we can go one better. First we have Google, then we have Newth, then we have Graham, then we have this.
Yeah, and I actually think Graham's number might be bigger than most Ackermann numbers, but I could be very wrong on that because Ackermann function, I don't know enough about it.
Mm-hmm.
But there's an XKCD where they plug Graham's number into the Ackermann function on both sides.
Oh, that's wild.
Large numbers exist because we seem to want them to exist. Vastness is something that seems to intrigue humans endlessly. Whether for religious, scientific, or just purely mathematical reasons, large numbers exist, and have always been, and will continue to be, a source of wonder and vertigo for humans who learn about them. I'm Sophia, and this has been Breaking Math. With me, we had on my mom, Diane Bach. Thanks for being on.
Thank you for having me.
Anything you want to plug?
I have nothing to plug except that this has been interesting and a weird exercise in feeling very, very small.
Yep. I can't think of a way to end this episode, so I'm going to end it by talking about how I don't know how to end it.